The earliest known compasses were made in China's Han Dynasty, between 300 and 200 BCE. These simple instruments were made from a lodestone, a naturally occurring, magnetically charged mineral that, when suspended in mid-air by a piece of rope, naturally points directly toward Earth's magnetic poles. Although these magnetized rocks were originally used for divination, owing to their seemingly supernatural qualities, they eventually proved to be an irreplaceable tool for people traveling across the globe. These compasses allowed navigators to orient themselves day and night, even when the skies were cloudy and other guiding lights, such as the North Star, were obscured. Earth itself is a magnet with two magnetic poles, just like the magnets stuck to your fridge, generated by the interplay between the planet's axial tilt, rotation speed, and movement of the molten metal at its core. A compass contains a tiny piece of magnetized material that is attracted to its opposite pole on Earth, which is located about 1,000 miles south of the geographic North Pole, due west from Canada's Ellesmere Island. So even if you're standing in the southern hemisphere, your compass needle will always point north. Where would the compass needle point in outer space? The answer to that question depends on where in outer space you're located. Earth's magnetosphere, the area around the planet where its magnetic force is dominant, is thought to extend about 23,000 miles toward the Sun and 230,000 miles away from the Sun. As long as you stay within this zone, the needle on your compass should still be able to register Earth's magnetic field and point you toward that spot in Canada. Beyond the outer edges of the magnetosphere, however, things get a little more complicated. That's because Earth isn't the only object in the solar system that generates magnetic force. Our Moon and Mars have magnetic fields, but they are far weaker than Earth's, meaning you would have to get pretty close to either one before they start affecting the bearing of your compass. If you're traveling even farther through the solar system, your compass is likely to point into the direction of one of two celestial objects. The first of these objects is Jupiter. Due to its high rotation speed, 28,273 miles per hour compared to Earth's 1,000 miles per hour, and massive metallic hydrogen core, about 1.5 times the size of Earth, Jupiter's magnetosphere is stronger than any other of our planetary neighbors, extending some 12 million miles around the gas giant. The second of these objects is the Sun, whose magnetosphere is bigger still, and encompasses the entire solar system. Unless you're within a planet's personal magnetosphere, like Earth's or Jupiter's, your compass is going to point toward the Sun. What's the point? Exactly which part of the Sun is hard to say, because the location of its magnetic poles changes roughly every 11 years. When sunspots produced during the solar maximum cause its magnetosphere to reorganize itself, Earth's magnetic poles flip polarity as well, but at a much slower rate, reversing every 30,000 years or so. The next reversal is due to take place within the next couple of centuries. Of course, while different celestial bodies will certainly have an effect on your compass needle, this does not take away from the fact that a traditional compass is useless for navigation in space, where compass holders can move in more directions than north, south, east, and west. That's why space agencies use special compasses known as vector magnetometers, which measure not only the direction a magnetic force is coming from, but also its magnitude, making them more useful than their earthbound counterparts. Don't forget to subscribe for more fascinating insights into the world of science and technology.